All right, so today we're going to talk about an algorithm that is, and I'm not exaggerating here, pretty much everywhere. From guiding the Apollo missions to the moon, all the way to the smartphone sitting right in your pocket. The Kalman filter is one of the most powerful and, well, beautiful estimation tools ever created. So let's dive in and see how this thing actually works.
To really get why the Kalman filter is so brilliant, we first have to wrap our heads around the massive problem it was designed to solve. And that problem is, how do you get a clear, accurate answer when all the information you have is, let's be honest, kind of messy and imperfect?
I mean, just picture this for a second. It's the 1960s. Your job is to get a crew of astronauts all the way to the moon and bring them back safely. The computers you have to work with, they have less power than a cheap calculator you'd buy today. All of your measurements from your sensors are noisy and full of errors. How on earth do you track where you're going accurately enough to pull that off? This wasn't just some classroom thought experiment. This was the real life-or-death challenge that NASA engineers were staring down.
And what's so cool is that this exact same problem, the Apollo problem, it shares its DNA with so many challenges we face today. Think about a self-driving car that goes into a tunnel and loses its GPS signal. Or your phone, trying to figure out its orientation by blending data from a shaky accelerometer and a gyroscope that tends to drift over time. They all boil down to the same fundamental question. How do you dig out the truth from a constant stream of imperfect, messy data?
Okay, so how do you solve this? Well, the secret actually starts with a really simple idea that we all get, taking an average. But, and this is the key, it's about doing it in a much, much smarter way.
So you could do what's called a batch average. You collect 1 million data points, you store them all, you add them all up, and then you divide. But what happens when you get one new data point? Well, you have to do the whole calculation all over again. For a spacecraft moving in real time, that's a total non-starter. The other way is the recursive average. With this, you just take your old average and you give it a little nudge based on the new measurement. It's incredibly fast, super efficient, and absolutely perfect when you've got limited computing power to work with.
And that right there, that is the core philosophy. We don't need all the data from the beginning of time. We can start with a guess, our belief about something, and then, piece by piece, one measurement at a time, we can keep updating that belief and get closer and closer to the real answer. This whole idea of iterating, of updating our belief, leads us straight into this beautiful two-step process that's really the heart and soul of the Kalman filter. You can think of it like a constant dance between what we think is going to happen and what our sensors tell us actually happened.
So, let's get official for a second. The Kalman filter is what's called an optimal estimation algorithm. Its job is to figure out the state of a system. That could be its position, its velocity, its temperature, whatever, by constantly cycling through those two key stages. It's designed to give you the absolute best possible guess, even when your measurements are full of noise and uncertainty.
And the whole process is just this simple, beautiful loop. First, it makes a prediction. Then, it gets new data and makes a correction. Predict, then correct, over and over and over again. And with every single loop, the filter's estimate gets sharper and more accurate.
Let's break it down. Step 1 is predict. We take our last best guess and we use a model of how the system works, basic physics, to predict where it's going to be next. So if we think a car is moving at 60 miles per hour, we predict that a second from now it'll be about 88 feet farther down the road. But because our model of the world isn't perfect, our uncertainty grows. A little bubble of possibilities gets bigger and fuzzy. Then comes the magic. Step 2. Correct. We get a brand new measurement from a sensor, say a GPS reading. Now that measurement also has its own uncertainty, its own bubble of possibilities. And what the Kalman filter does is pretty incredible. It mathematically fuses these two bubbles together, our predicted bubble and our measurement bubble. And here's the amazing part. The result of that fusion, our new estimate, is a new bubble of possibility that's actually smaller and more precise than either of the two we started with. So our new best guess is more certain than our prediction was, and it's more certain than our noisy measurement was. It's not a compromise, it's truly the best of both worlds.
Okay, so this all sounds fantastic, but how does the filter actually do this? How does it decide what to believe when it's fusing those two pieces of information?
I mean, that's the real question, isn't it? If your prediction says the car is at mile marker 10, but your kind of flaky GPS says it's at mile marker 9.8, where do you put your final guess? Well, the answer comes down to one word: trust.
This is where the secret sauce comes in. It's a value called the Kalman gain. And you can just think of it as the filter's brain, or maybe like a dynamically adjusting trustometer. It's not some fixed number. The filter calculates it fresh at every single step.
and its whole job is to tell the filter exactly how much to trust the new measurement versus how much to trust its own prediction. And the logic behind it is just, well, it's just common sense. If your new measurement is super noisy and all over the place, that means you have low trust in your sensor, so the Kalman gain will be low, and the filter will say, you know what, I'm going to mostly stick with my prediction. On the flip side, if your prediction model itself is very uncertain, the Kalman gain will be high, and the filter will say, okay, I'm going to pay a lot more attention to this new measurement. It's this beautiful, constantly adapting balancing act.
So let's just zoom out for a second. This whole elegant mathematical dance of predicting and correcting, it has had an absolutely massive impact on the world we live in.
The journey of this thing is just incredible to think about. In 1960, Rudolf Kalman publishes his theory in a pretty dense academic paper. Just a handful of years later, NASA engineers are adapting it to literally steer a tiny metal can all the way to the moon. And today, that very same core idea is humming along silently inside devices all around us.
And when I say it's everywhere, I mean it's everywhere. It's in your car's GPS, making that little blue dot move so smoothly on the map. It's what helps drones and self-driving cars stay stable and know where they are. And yes, it's inside your smartphone, constantly fusing the noisy data from the accelerometer and the gyroscope so that your phone always knows which way is up. It is, without a doubt, one of the foundational algorithms of our modern technological world.
You know, this quote from Dr. Shane Ross just nails it. It perfectly connects this seemingly complex algorithm back to a simpler idea. He says it's basically just a filter that smooths out noise, but it's a really, really smart one because its weighting, that alpha he mentions, which is our Kalman gain, is changing at every single step to give you the absolute best result possible.
So in the end, the Kalman filter teaches us this really powerful lesson about how to find a clear, reliable signal in what is often a very noisy and uncertain world. And it kind of leaves us with a final question to chew on, doesn't it? What's the next seemingly impossible problem out there that we could solve if we just find the right way to smartly and iteratively fuse together our imperfect information?